Well, hello, welcome again to our journey into linear algebra. And in this section we're going to spend a number of videos looking at the Jordan form. Now, I'm going to do this not in an overly formal way, but enough so that you can see what's happening and why it's happening. So in our previous work in linear algebra, when you did eigenvectors and eigenvalues and diagonalization, you saw that a square n by n matrix is diagonalizable if A has a full quota of n linearly independent eigenvectors. And that is, you can plug those into a matrix P, which is then invertible because the independent eigenvectors are linearly independent, and there are n of them. And you can get a diagonal matrix D, so that with a change of basis from a standard basis to an eigenbasis, you can show that P inverse AP gives you the diagonal matrix. And from that, you could then calculate the nth power of the matrix A. So just as a quick reminder of how that works, I've just done an example here. We've got a matrix A, which is 3, 2, 2, 3. We want to calculate the nth power of that matrix. So here's the worked example for this. So here's our matrix A. You can probably, I hope, guess that one of the eigenvalues is 1. If you subtract 1 off the main diagonal, the determinant's obviously 0. And then from the trace, the sum of these two has to be the sum of the eigenvalues. So the other eigenvalue's got to be 5. We get the eigenspace for 1. So subtract 1 off the main diagonal. And then the eigenspaces will have one of those minus one of those, so it's 1 minus 1, the span of that vector. And the eigenspace for 5, you subtract 5 off the main diagonal, gives you this, and you get the span of 1, 1. So you whack these into your P matrix. The diagonal matrix will be in the same, the eigenvalues in the same order as the eigenvectors, so you get 5 and 1 here. And finally then P inverse AP is D. And so I can undress the A, I can multiply the P on this side and the P inverse that side, and then take the nth power of that. And as you've seen, when you do that and you write this out n times, all the P's and P inverses cancel in the middle, leaving you 1 at one end and 1 P inverse at the other. So I've quickly just calculated that. There's my P. Now the nth power of a diagonal matrix is easy because you just raise the entries to the nth power, 1 to the n being 1, multiply by the inverse of P, and I've just finished that off here, and there it is. And you can check that this works because, for example, if you put n equal to 0, then you'll get 2, 2, 0, 0, and you divide by 2 gives you the identity. And if you put n to be 1, you'll get 6 divided by 2 is 3, 4 divided by 2 is 2, and that gets you, of course, back to the matrix A that you started with. So that all works beautifully, provided the matrix has an inverse. Provided the matrix has n linearly independent eigenvectors. Unfortunately, as you're probably aware, not every matrix is diagonalizable. So, for example, this fairly harmless looking matrix here turns out not to be diagonalizable, and we can show that very quickly by just calculating the eigenvalues and eigenvectors for this one. Now this turns out only to have one eigenvalue, and from the trace you see it's going to have to be 5 because 5 plus 5 is 8 plus 2. And the eigenspace for 5, when you subtract 5 off the main diagonal, gives you this, which is the span of 3 minus 2. So there's only one eigenvalue, and you only get one eigenvector, so and the dimension of the eigenspace is just 1. So the A then is not going to be diagonalizable because it doesn't have a full quota of eigenvectors. So that's where the situation where we really like diagonal matrices, because you can do what we did up here and calculate nth powers of matrices. And so we'd like something that is we'd like to be able to do something with non-diagonalizable matrices, and that's going to lead us to the Jordan form. So the key to deciding whether or not a matrix is diagonalizable is the concept of multiplicity. And there are two types of multiplicity. We have firstly the algebraic multiplicity of an eigenvalue lambda, that's its multiplicity as a root of the characteristic equation. So here I'm using the word multiplicity in the standard sense when talking about polynomials. So for example, if I have a characteristic polynomial for some matrix A turns out to be this expression, so this would of course then be an 8 by 8 matrix. So this has got eigenvalues 3, minus 2 and 1, and the algebraic multiplicities are for each one of them are respectively 4 for 3, 3 for minus 2 and 1 for 1. So that's the algebraic multiplicity. It's the normal multiplicity of the root of the characteristic polynomial. The geometric multiplicity of an eigenvalue, lambda, is the number of linearly independent eigenvectors associated with that eigenvalue. In some cases, you can have a situation where you have an eigenvalue which occurs twice in the characteristic polynomial, and it actually gives you two linearly independent eigenvectors. And sometimes it only gives you one linearly independent eigenvector, as we saw in the 2 by 2 example above. So clearly the geometric multiplicity has less or equal to the algebraic multiplicity, and given a square matrix A is diagonalizable if and only if the geometric multiplicity of each eigenvalue is equal to its algebraic multiplicity. So as an example, here's a nice 3 by 3 matrix. We're going to calculate the eigenvalues, and for each one their algebraic and geometric multiplicity. So here is the solution to this. Here is our matrix B. And without further ado, I'm just going to tell you what the eigenvalues are. I'll leave you to calculate them. It turns out they're 2, 2 and minus 1. You can check that makes sense. If you add up, take the trace of this, you get 6. And if you add up these, you get 3, I should say. And you add up these, you also get 3. Now, the eigenspace for 2, so 2 has algebraic multiplicity 2. It occurs twice in the characteristic polynomial. And the eigenspace for that is the kernel of this matrix, so I just subtract 2 off the main diagonal. And this matrix has rank 2, nullity 1. So this has, the rank is 2, and that tells me the nullity is 1. So there's only one eigenvector hiding in here, and there it is, it's 1, 0, 1. Now the dimension of the eigenspace for minus 1 has to be exactly 1. You must get at least one eigenvector from this one, and you can't get any more because the algebraic multiplicity of this is just 1. So as a little summary here, there are the two eigenvalues. 2 has algebraic multiplicity 2, but geometric multiplicity only 1. Minus 1 has algebraic multiplicity 1 and geometric multiplicity 1. And that tells me this matrix B is not diagonalizable. So B is not diagonalizable. Okay, so that's the story thus far. What can we do with these matrices that are not diagonalizable? So what do we do in this case? Well, I'm going to look at one very special case, one very special situation. So we're going to suppose we have a general n by n matrix, but it has the property that it only has one eigenvalue. And it's got one eigenvalue, so the algebraic multiplicity of this is n, but the geometric multiplicity is only 1. So that means this matrix, this n by n matrix, only has one eigenvalue, and it only produces one eigenvector. Now, very, very, very important example here, because this particular example here is going to lead us to our theory of the Jordan form, at least in this particular case. And once we understand what happens in this case, then we'll see how to generalize it to other cases. So, apropos nothing, I'm going to say, suppose we can find a linearly independent set of vectors v1 up to vn with the following property. So a v1 is lambda v1. So that means v1 is an eigenvector. Now a v2 has the property that when you multiply a by this vector v2, you get lambda v2 back again, so it's almost an eigenvector, but you get plus this vector v1 we had up here. Vector v3 in my list has the property that when you multiply by a, again you almost get an eigenvector, you get lambda v3, but you pick up plus v2, which is this vector we had up here. And so on all the way down, and finally a vn is lambda vn plus vn sub minus 1. So we get this sequence of vectors. I'm not telling you how to get these at the moment, we're just saying suppose we can find this set of vectors v1 up to vn. v1's an eigenvector, and all of the other v's satisfy this condition, that you multiply by a, you get back lambda times the vector you started with plus the previous vector in the list. Now I'm going to put these vectors into a P matrix, just as we did with the eigenvectors. By the way, these are going to be called generalized eigenvectors later on. So we whack these into a P matrix, so P is this thing here. And now I'm going to calculate A times P. So when I let A hit this matrix here, I'll get A v1. Now v1 was an eigenvector, so that gives me lambda v1. We're going to get A times v2, and A times v2 up here was lambda v2 plus v1. And similarly, a v3 is lambda v3 plus v2, all the way up to the end, lambda vn plus v sub n minus 1. And now comes the interesting bit, because now I'm going to rewrite this matrix as a product of two matrices. I'm going to write it back as my P matrix that I started with here. And now I see, well, what's got to go here to make this multiply by this to give me this? Well, I'll need a lambda times v1 to give me lambda v1. For the second column, I'll need one of these plus lambda times this one. So I'm going to get lambda, I'm going to get v1 plus lambda v2. So v1 plus lambda v2. For this one here, I don't want any of those. I want a v2 plus a lambda v3, so I'm going to get 0, 1 lambda and zeros below, all the way down to the end. A times vn is lambda vn plus 1 times the term before it, which is v sub n minus 1. So we can see that AP then, which got me this, can be factorized into this form, and that simply means that AP now is P times this matrix here, which I'm going to call J. Now just enjoy that matrix J. Look what it says. It's got the eigenvalue all the way down the main diagonals, zeros below, zeros above. It's almost diagonal, except I have these little ones floating gently above the lambdas just off the main diagonal. This matrix J we're going to call a Jordan block or a Jordan form for the matrix A. Now, since the vectors in these vectors, v1 up to vn, we assumed were linearly independent, and that means this matrix P is invertible, and so we can write P inverse AP as J. So it's almost diagonal. It's almost diagonal, except we've got ones floating above the lambda on the main diagonal. So it's very close to being diagonal, except for the ones. So this Jordan form, this Jordan block, is going to be the analog for a diagonal matrix, and this P matrix is going to be the analog for our matrix of eigenvectors. So this is just, now I haven't told you how to get any of these V's or anything. I'm just saying suppose we can find a set of V's with this property, then this is what it does for us. And we'll get to the question of how we find these V's in a moment, and we're going to give them some names. So the above example suggests that the right, in inverted commas, generalization of a diagonal matrix is a Jordan block. So hence, I'm going to define an n by n Jordan block based on the eigenvalue lambda to be this matrix. So with lambdas on the main diagonal, 1's just off the main diagonal, we're going to call that J sub n. It's an n by n matrix based on the eigenvalue lambda. Now this Jordan block has some very interesting properties we'll have a look at firstly before we work out how to construct these vectors v1 up to vn. So before we look at that then, how to obtain it, we'll look at some of its properties, and in particular we're going to be looking at the powers of a Jordan block. And we'll do that in the next video. We'll have a look at what happens when you start working out powers of a Jordan block.